be walking you through an overview of the circulatory system, and I'll help you understand how the structure of various arteries, capillaries, and veins relates directly to their function, right? After all, this class is called Anatomy and Physiology, and that means structure and function, and the structure is always related to the function. Here we go, chapter 21, blood vessels, blood pressure. I like this picture. It really helps us to see that the systemic circuit is sort of paralleled within the structure of the arteries and the veins. So I'm not talking about these ones right now. These are the pulmonary vessels. Remember, they send blood from the heart to the lungs to get reoxygenated, and then they come back in. This chapter, we're really focusing more on the systemic circuit. So this is starting with the aorta, and every time the powerful left ventricle pushes blood out through that ventricular ejection phase, it pushes blood into the aorta. And so sort of spurt at a time, the blood sort of piles up and is pushed by pressure through all of these many, many miles of vessels. What we don't see in this particular image is that at the end of each of those arteries is a capillary bed. Capillary beds are made of the very tiniest blood vessels, capillaries, and these are the only vessels that are permeable enough to allow for gaseous and nutrient and waste exchange. Even the next smallest, these arterioles, or certainly these very large vessels like the aorta itself, are far too thick to allow for oxygen to diffuse through or for wastes to diffuse into. It is only the capillaries down here, very, very thin, transparent structures. Many of them are smaller in diameter than a red blood cell, which, remember, relates to that foldability of our red blood cells and their ability to fit into those tiny spaces. All right. So, as I was saying, if we were to follow the aorta downstream, we could come all the way here. This one's called the lateral femoral cutaneous artery, and then there would be a capillary bed right here. So in this particular part of the outer thigh, it receives blood from this particular blood vessel. And then the capillary beds, although they're not shown in this image, would connect this little tip of this arteriole to this little tip of this blue venule so that the blood has a return route to get back to the heart. The same can be said about any part of the body. There is a way to get there and a way to get back. Let's look at the big toe. Could we get from the heart to the big toe? Sure. Does the blood pressure push oxygen and nutrients in the blood all the way to your big toe? Naturally. Your big toe is alive and metabolically active, and so it's generating waste and carbon dioxide, which will then follow more or less a parallel path, but this time back through the veins, and in this case into the heart through the inferior vena cava. So look at that. Every cell in your body has an artery or capillary bed ultimately delivering nutrients and waste, and every cell in the body has its own little sort of sewer system, the venous system, which helps to return the blood to the heart. This is one of the most important images that we see in this PowerPoint, really laying out a lot of detail and helping us to understand how the structure of a very large muscular artery, like the aorta, might differ from a vein like the great saphenous vein. So let's take a look at the different layers, and then we'll sort of bounce back and forth between these different images. I wanted to separate the arterial and venous portions of the systemic circuit for you, and so I used these two pictures. It's helpful when we're trying to conceive this idea to see them together, but it's a lot. It's really busy, and so here we get to spread them apart, and that's really our major task in lab in the next week. is to be able to visually identify these. So I strongly encourage you to be attending Open Lab, and when you're at home using coloring books or making your own unlabeled versions of these images that can really help wire these things into your brain. That's not what this particular lecture is about, though. This is more about the nitty-gritty detail. Okay, so here we go. 3 major types of blood vessels: arteries, capillaries, and veins. Arteries always carry blood away from the heart. So in my mind, I think the AAA rule: arteries always away. And that reminds me, even if we're looking at the pulmonary circuit and the color is different, that at least that function and that direction is the consistent rule. We can see that they're thick, elastic, and muscular, and that they will branch into progressively smaller and smaller vessels called arterioles. I always want to say this with an Italian accent. It looks like a pasta to me. Arterioles. But maybe it's just me. So, what do arteries really do for us? They help to contain this very high blood pressure. Every time the left ventricle contracts, the aorta, remember, swells a bit like the throat of a frog. It must be very elastic so that it doesn't fracture or begin to scar as it expands and contracts. Not necessarily actively like the heart, but passively, because it's receiving that spurt of blood we call a bolus. So when the left ventricle contracts and we are in the ejection phase, the blood is being ejected into the aorta. And my point is, look at all these little blue squiggly lines. These are called elastin. And just like the elastic in your undies, they can stretch, but they will recoil, tightening back to their pre-stretched state. That is mission critical, ladies and gentlemen. We need the aorta to be very compliant, very stretchable, but we also need it to be very elastic so that it squeezes down on that blood as soon as the ventricle relaxes. Of course, that pressure differential here will close the aortic valve. But it also helps to push blood downstream. Once that aortic valve is closed, just like what we had seen in the heart, where the valves prevent backflow, this is very important. We just spent a lot of energy pumping the blood out of the heart. We need that aortic valve to close so that the blood cannot go back into the heart, but instead must go out into all of these many blood vessels, perfusing the brain, the arms, the organs, etc. Moving down, we see that if we were to follow the aorta into a smaller vessel, like this one here, the left common carotid. This is a very important artery, of course, because not only is it supplying oxygen and nutrients to your head, face, and neck, but it will split into this one here, the left internal carotid, which perfuses your brain. In case you missed this, when I say perfusion, I'm really meaning that blood is flowing through the capillary bed. Perfusion allows nutrients and oxygen to be pushed through the capillary bed, where we're going to see gaseous exchange between O2 and CO2 and nutrients and wastes. Here, remember that capillaries are the only vessels permeable enough to allow for this exchange. And when we talk about the blood flowing through that tissue, we're really talking about this concept of perfusion. Okay, so after the aorta, we move into these smaller arteries. Not only are they smaller, but they have a different structure to them. Look at the difference between these. Maybe this is the aorta, maybe this is the internal carotid. Notice that there is this middle layer of muscle right here. We have the tunica media. Although we're labeled tunica media here, which literally just means the middle coat, the inner coat, the outer coat. The tunica media is where the smooth muscle is. Although in the large arteries like the aorta, there is a significant amount of elastin, there is also a significant amount of smooth muscle. And look at this tiny yellow bit. This is a nerve from the autonomic nervous system. This is a sympathetic neuron, which in a situation of low blood pressure or a situation of emergency, this nerve will zap this artery into action. Can you imagine what would happen? The smooth muscle is going to squeeze down, constricting this vessel. We call that process vasoconstriction. And you can't directly control it, unlike skeletal muscle where you have some voluntary control of when you move your arm or when you move your mouth. You don't have direct control over this. This is an autonomic function. Now, that being said, through feedback and meditation, sometimes we can learn to dramatically affect the autonomic nervous system, but it's still technically an indirect effect. Okay, so the tunica media, what type of tissue is this? Smooth muscle. When we zap it, it tightens, constricting or decreasing the size of the opening. To speak very scientific terms, we would say pressure towards the center decreases the size of the lumen, and therefore the blood volume. However, blood pressure will increase, right? So if we think about it, if you have fluid in a container, you squeeze that container, the volume can go down as long as there's a little gas in there, and the pressure goes up. This is exactly the phenomenon that we're talking about with blood pressure regulation. It is this layer, the tunica media, that can affect blood pressure by squeezing. Okay, the tunica interna looks like a toilet paper tube in this particular scheme. We can see the inner layer all by itself down here at the capillary, because the capillary is nothing but that innermost layer. Here's the phrase, the most important concept so far. Capillaries are the only blood vessels permeable enough to allow for gaseous and nutrient exchange. Now you see why. There's no thick collagenous outer coat to contain the pressure. There is no smooth muscle middle coat that could interfere with diffusion. Even these tiny arteries that are very thin still contain that outer, middle, and inner coat. In the capillaries, nothing but inner coat. Okay, so what is the inner coat? Endothelium is to the blood vessel what the endocardium was to the heart. Histologically, the endothelium is a single layer of cells. Remember, this is called simple squamous epithelium. We can see the nucleus in cross-section here, and we can see where one cell meets up with another. These intercellular clefts are not totally impermeable, by the way. So we'll see that things can leak out through those cracks, and it is supposed to work that way. What else do we see? Like all epithelium, there is a lumen on one side of the cell and a basement membrane on the other side, right? Epithelium has to be connected to the rest of the body, and it is connected through this basement membrane. Love this phrase. Makes perfect sense to me. A membrane is sort of a sheet, usually collagen, some sort of connective tissue like plastic wrap. And this one is the basement membrane, and that's because the cell, like a house, has the sky above the opening, the lumen, and the basement below, just like my house. Is your basement on top of your house? No, of course not. So here's a great structure-function connection. Why are capillaries the only vessels permeable enough to allow for nutrient exchange? It's because they're so darn thin. And if we could do a magic school bus thing, we could park right here. I would flash the high beams on the wall, and no lie, they're so thin you would see right through them, like cellophane or like those transparent rice noodles. Here you can see a red blood cell. In this one, it's a little hard to tell. Maybe the red blood cell would be able to fit through without folding. There are certainly cases where the capillaries are slightly smaller, in which case this biconcave shape facilitates a folding. It folds like a little toilet seat or a little taco shell, and then it can easily fit in there. Why do we want the red blood cells to go through the capillaries? Oxygen delivery, right? Okay, moving a little bit back and forth here now. We've gone through the aorta and say into the common carotid, and now we're up into the brain, and these are the capillaries that are nourishing your brain right now, so you can understand this amazing structure function connection. Next, we see that the capillary beds begin to converge. So whereas the arterial side is something like a tree, starting with large vessels that branch into progressively smaller and smaller ones, the venous side, where it goes blue and then heads back towards the heart, this is more like a river system, right? These are little trickles, and this is some tiny little creek, and then here's a river, and then here's a big Mississippi. Okay, so that's a subtle thing, but an important thing to keep in mind, that when blood is flowing in this direction, it is continually moving through smaller and smaller and smaller vessels until it can just barely fit through. But once the blood begins to return to the heart, it flows into larger and larger and larger vessels and has an easier time passing back into the heart. What are those smallest veins immediately downstream of the capillary beds? Venules. Venules merge and become larger medium veins. Notice these have valves like the heart. And then those medium veins eventually flow into these very large veins like the vena cavae. So looking over here to give some true-to-life context, let's look here. In your hand, blood returning from the capillary beds in your palm flow into this long cephalic vein, and maybe they squirt across through this one called the median antecubital into the basilic, into the subclavian, into the brachiocephalic, and then the superior vena cava. Whereas on this side, we started in the heart and we went from larger veins to smaller ones. I'll trace that same path. How does blood get from the heart to the palm? Here, from the aorta to the brachiocephalic trunk to the subclavian, axillary, brachial, and then either through the ulnar or radial to the palmar arches. So again, this concept and the ability to visualize these pathways is very important, and you need to spend quite a bit of time thinking about it. It will help you to really learn these. I understand the tendency to just blindly memorize, and I'm not diminishing the work that goes into that, but don't lose sight of the big picture. You are going to be healthcare providers, people. You may have patients with peripheral vascular disease or deep vein thromboses or PICC lines, or at the very least, you're going to have to do a venipuncture. And so you got to know where the median antecubital vein is, and it's very important that you understand how blood flows through the body. Finishing up this very first lecture, let's see. When we look at the structure of a capillary network, remember that these arterioles are the smallest arteries that have the three layers, outer, middle, and inner coat. But look at what happens when they branch into smaller vessels. Here is the so-called capillary bed or capillary network. We see that there is a main thoroughfare channel that goes right through. Right, this looks like so many neighborhoods. There's sort of a main road to go right through the neighborhood. And then, if you're trying to find your friend's house, you take the second right off of that main thoroughfare and then find his little cul-de-sac. So, the thoroughfare channel is the straight connection, the direct connection between this arteriole and this venule. Notice that the blood changes color as it passes through the capillary network. Although we don't see the oxygen and carbon dioxide labeled, we know that what is happening here is that these capillaries are delivering oxygen to the hungry cells, and that these cells are dumping their carbon dioxide into the blood to be hauled away. If that doesn't happen, this tissue becomes quite acidic and toxic for the cells. What are the other capillaries then? If not the thoroughfare channel, these other ones are sometimes just called true capillaries. And if they're on this side, they are arterial capillaries. And if they have turned blue, then they're venous capillaries. Structurally, these are really identical within their given class, which I'll show you in just a second. Two quick things before we finish up this first video. Substances typically move through capillaries by diffusion or osmosis, which is technically diffusion of water, which is why it says that right there. Look at capillaries are permeable and leaky. When I say permeable, I mean things are going through the plasma membrane, just like we had learned in previous chapters. Remember the list of things that can pass through the phospholipid bilayer, the things that cannot pass through? That's where you want to plug that information in. What kinds of things could leak right through the cell like it goes through a wall? Oxygen, carbon dioxide, water, and fats like steroids. What kinds of things can't get directly through and therefore might need to leak out in between these intercellular clefts? That's really what I'm meaning here. Larger water-soluble molecules, these are polar molecules, which would typically be on our red list, and then ions, and some proteins, and believe it or not, in some cases, even whole cells can crawl through these little cracks, like white blood cells seeking out the site of an infection. So capillaries are both permeable and leaky, and it is normal for them to be so, and there are a whole host of mechanisms that our body uses to change it. So during one phase of your day or one metabolic state, maybe your capillaries are not very leaky. However, when you start to exercise and build up waste in the tissues, the capillaries will actually begin to expand a tiny bit, allowing more oxygen and fluid to nourish this tissue and allowing for more waste to come in. Think about a really extreme example like a sprained ankle or an infection. We see huge bulk swelling called edema. And edema is really the result of these capillaries being made super leaky by chemicals like histamine well, I can't think of another one right now, but that's a great example. Think allergic reaction and why you get all swollen after a bee sting, or how someone with a peanut allergy can have their face really, really puff up. The point I'm trying to make is these capillaries are dynamic, and the leaky quality can be up or down regulated through hormones. Different types of capillaries too. 3 different types of capillaries. Continuous capillaries. In this cross-section, we can see where one endothelial cell meets up with the other. There is just a tiny crack. In some cases, these are sort of stitched together. In many cases, the crack can kind of expand or shrink depending on those chemical factors. Fenestrated capillaries. Fenestrae are like little bullet holes. Look at this. The plasma membrane, or the cytoplasm in the endothelium, is squeezed out, so there's nothing but that phospholipid bilayer here, the diaphragm. And so you might anticipate that these are even more permeable than what we would see before. In some cases, they're fenestrae without a diaphragm. These are just little paper punches, little bullet holes right through here. And so these are extremely leaky. And we find these in places like the kidney and the small intestine, where we have a lot of fluid exchange. In the kidney, of course, it's during urine formation. And in the intestine, it's during nutrient and water absorption from our diet. But in either case, we would need an extra leaky one. These ones, which are the most common, the vanilla capillaries that we see in all places of the body, they're less leaky. These are more leaky, and we find them in a couple special places where we need the extra fluid exchange. And then these ones, sinusoidal capillaries. Look at the gaps here. They're so big that entire blood cells can come in and out. And of course, these are found in the bone marrow and in the liver, places where we do want blood cells, particularly red blood cells just being created, or White blood cells just entering circulation to go to work, they need these very large openings. Okay, let's see a different visual representation in a future portion of the video. Here's another summary here on slide number 8, continuous, fenestrated, and sinusoidal. And I think in your book they have maybe some better images. Don't be afraid to use some of these terms as your search terms on Google Images. You might find some really good pictures that resonate with your particular learning style a little bit better. Last few slides, I'm not going to read these to you, but you can see the details that I expect you to know on this so-called inner coat. I suppose the main point here is that this one is super slippery. This is the non-stick coating that prevents platelet aggregation. It prevents blood clots from forming, and you can think of it as a Teflon coating of the interior of the blood vessel. This should sound familiar because the endocardium, the inner lining of the heart, is made of exactly the same tissue. So it's a little bit artificial for us to say that one is different from the other, when it turns out that if we were right here in the left ventricle, this would be endocardium, and if we could run our hand along the inside of the wall just over the aortic valve, we would come right back onto that smooth, slippery layer. It is histologically the same. It's just an arbitrary change in the name, like South Dakota and North Dakota. The prairie doesn't know the difference, right? In that very same way, this endothelium is really continuous throughout the entire circulatory system, including inside the heart. Tunica media, we talked about this, the muscle layer and its ability to squeeze down or to relax. And this is at the absolute foundation to understanding blood pressure regulation. If your blood pressure is too low, your brainstem zaps the tunica media and it constricts. Vasoconstriction, increasing the pressure. Well, why don't we want that all the time? Well, it's the downside. You're going to deliver less blood to the tissue if you're vasoconstricting. So you can keep your blood pressure up, but you got to balance it with the ability to deliver and haul away the trash. And so we can also just relax if they're too tight through an opposite process called vasodilation, where the lumen increases. Blood flow also increases. But what's the downside? The pressure falls. And so this is what we see in many times in our patients when they pass out. They see blood, or they're too emotional, or they're suffering from some cardiovascular dysfunction, and they get lightheaded and they fall over, right? So here's the downside. Although they may have lots of blood flowing to their tissue, it's flowing very slowly, and there's not enough pressure to keep blood flowing up to their head. And so they fall down. It's not really funny. The tunica externa, oftentimes called the adventitia. This is like the sausage casing. Very thin, very tough collagen coating to hold the vessel together. So this is maybe going to sound weird, but listen to this. You know what a brat looks like, right? It's sausage with a casing. Well, what do you call a brat without the casing? A meatball. Okay, so it's like a blood vessel, people. Just follow this, if you will. If a blood vessel doesn't have the sausage casing, it begins to expand and fall apart. And this can result in a life-threatening condition like a hemorrhage or an aneurysm. So we want our blood vessels to be like brats, a nice casing holding everything together. In very large vessels, there needs to be extra blood supply to the vessel wall itself. And we can see that here. These vasa vasorum are to the muscular arteries what the coronary arteries are to the heart. Now think about that. Even though the heart is full of blood that's circulating, the heart is too thick for the blood inside of the ventricles to nourish the myocardium. In the same way, your aorta, your brachiocephalic trunk, your common carotids, or iliacs rather, are too thick for the blood flowing through the lumen to nourish the blood vessel itself. And so periodically there are these little recurrent branches which come out and then dive back into the muscular wall and the adventitia to keep the vessel alive itself. Holy cow, is that a lot? Why don't you pause the video here and see if you can answer these questions.